Okay, so I'm going to just show you the circuit. Okay, so you need a current source. You type current. So you get the current source here, and then you take the components. So you need a resistance here, then you need an inductor, and then you need a capacitor. Okay, so they need to be connected in parallel. So you take the wire, make these connections. Okay, and then like this. Then you need a ground. Always there should be a reference, and the reference voltage is taken as 0. So that is what we call as ground. Now, if at all we have to do anything, you need to assign value for these resistances. So R1, let's say, so we put 10, I think, in the last class. So let's put the same value, 10 ohm. L, I think we put 10 millihenry. Entry, even if you don't put the unit, it is okay, but you have to put whether it is milli or micro, that you have to put. And this one also 1 milli, 1 millifarad, 1 millihenry, and 10 ohm. So this is the parallel RLC connection, and then we have one current source. Now the direction of current is shown here. For AC analysis, we take AC current source. Okay, so here we have what is called as the small signal analysis. So we can give some amplitude. So let's say 1 milliampere we are giving. So amplitude you have to specify, frequency also you have to specify. Okay, so that for AC analysis, that is not required to specify your frequency, because frequency is a variable. But if you are using transient analysis, if you want to see the waveforms, then you have to specify what is the wave, what is the frequency that you want to see, say 200 Hertz. So I have specified this that the current source is basically generating a sine wave, and specified its amplitude, its frequency. So that is the first line. Second line is necessary for doing the frequency analysis or AC analysis. Now to do the analysis, you click on Run, then you go to AC analysis. So here there are some options. So this is what I think you were asking, right?
Yes,
what are these? Okay. So these are basically the way in which you want to sweep the frequency. I mean, the graph is usually drawn, frequency analysis graph is usually drawn in a logarithmic scale. What do you mean by logarithmic scale? Why do we use logarithmic scale? Because we want to show a large range of frequency. say from 1 Hertz to say 10 kilohertz in lot of details. If you use a linear scale and if you are drawing it, and if you want to show the detail, it will require a very large length for the graph, because if you say one division is equal to say 1 Hertz, and if you start doing like that, 1 Hertz, 2 Hertz, 3 Hertz, 4 Hertz, then 100 Hertz, 101 Hertz, 102 Hertz, it keeps on going, like 999 Hertz, 1000 Hertz, like that. If you keep on increasing the length, it would require a very large length. So a more convenient way of showing details of low frequency as well as high frequency, but in a limited length, is to use a logarithmic scale. In logarithmic scale, what we do, we start with 1, and after a fixed distance we say 10. So we give a 1 unit displacement in the graph to be the multiplication by a factor of 10. So that is what decade means. Okay, from 1 to 10, that is 1 decade. 10 to 100, another decade, and then 100 to 1000, another decade. 1000 to 10,000, another decade. So we require only 1 to 10, 10 to 100, 100 to 1000, 1000 to 10,000. So 4 decades only we need. So five points which are equally spaced is how you show 4 decades. And if it is octave, that is yet another way, like you go in by factor of 2. So if you are starting with 1, then you go to 2, then from 2 to 4, that is like a unit distance, and then from 4 to 8, another unit distance, 8 to 16, another unit. So it's like multiplication by a factor of 2. In musical scales, octave is a very important way of showing frequencies, because the sounds have some relationship when it comes to harmonics. So like if you see a piano sound, there is A, B, C, D, and then there is a higher version for that, that is a next octave. Like there is again a repetition of A, B, C, D, E, F, right? So or A, B, C, D, E, F, G, and then again A, B, C, D, E, F, G. So like that it goes to the next octave, and again next octave. So it's like multiplication by a factor. If you look at the frequency, it is like multiplication, like they are harmonics basically. So these are linear, means that is what I said in the beginning, the normal one. Okay, so but that would require a very large length in the graph. So in frequency response plot, we preferably in electronics we use decade. The x-axis, the frequency variation, will be shown in decade, and then where to start, that will be say 1, where to stop, say 10k. Okay, and it has to be sufficiently taken. You can start from point 1 also, end at say 10 mega also, but where to start, where to stop, we usually decide by recognizing where is our resonant frequency. So there should be sufficiently, like 1 or 2 decades before resonant frequency and 1 or 2 decades after resonant frequency. Okay, so you can start accordingly. But all of this like go in by factors of 10. Now number of points per decade. So if you want your graphs to be very properly drawn, because the simulation will evaluate the value of voltage, current, etc. For only finite number of points in a given decade, and that how many points you need, you have to say 100 or 500 points. So if I say 500 points in one decade, there will be 500 points, and each 500 points means each of those frequency it will find the voltage and then join it with a line, and then it go to the next decade in another 500 points. So each decade will have 500 points. So these are the specification you have to give. Okay. So once you specify that, then you can look at what is the current, voltage, etc. For example, if I want this voltage here, okay, so you can see now the x-axis, if you look, it's very clear, right? Now 1 Hertz, then 10 Hertz, then 100 Hertz, 1 kilohertz, 10 kilohertz. So this is how it is showing. So it has details as small as like 1 to 10 Hertz. It has a large amount of detail which we would have missed if at all we are plotting it in a small paper of this same size, but up to 10 kilohertz. If you have to do it in a linear axis, how will we will take it as 2 kilohertz, then 4 kilohertz, 6 kilohertz, 8 kilohertz, and 10 kilohertz. So that is how we will divide it. Or if there is only 4 divisions, we will say 2.5 kilohertz, then 5 kilohertz, 7.5 kilohertz, and 10 kilohertz, like that. Okay, but here you see that it gives you detail of low frequency as well as high frequency. Now right side is showing the phase variation. So phase variation, if you don't want, you can suppress it. So to suppress it, you right click and say don't phase. So we are basically concentrating on the magnitude. So it has magnitude detail and the phase detail. Okay. Now the x-axis, if you look at again, this is decibels. So decibel means voltage. Whatever voltage is there at that point, we take basically log to the base 10 of that voltage and multiply it with 20. Now you can right click here on that scale and you can say that you want it linear. So voltage, it is better to show in linear, okay, but frequency we will show it in decades. So if I show like that, then you can see how the voltage at the point varies. So what you can see, we are injecting some current into this parallel node, and what is happening is that the voltage is maximum at a particular frequency, and it reduces for low frequency and it reduces for high frequency. So what is a simple reason we can give for it? We have R, L and C in parallel. So when you inject a current, so this is a constant current source. Constant current source means this is a AC ideal current source. So the value of current is entirely decided by the source itself, but the voltage is variable. That will be determined by this current that we are injecting into the node and the value of these components, the impedance offered by each of these components. There are 3 components in parallel. One is resistance. So the current, when you inject a current into this node, depending upon which branch has low impedance or low resistance path, so maximum current will pass through that path, and so that way the given current will be divided into 3 parts. So the one with the higher impedance will have lesser current, but a higher contribution of current will go through those paths which offer less impedance. We know for very very low frequencies, inductor offer like a short circuit. So majority of this current will, for low frequency, if the frequency is very low, say 1 Hertz, then most of the current will be flowing through this. It's like a short circuit. So most of the current will flow through this inductor, and capacitor offers a very high impedance, and almost negligible current will flow through the capacitor. But when you go to high frequency, what happens? The capacitor will act like a short circuit, and almost all the current will bypass through the capacitor, and that is why again parallel combination impedance is determined by the smallest of the 3, right? So at high frequency, the parallel combination impedance will be decided by capacitor. At low frequency, it is decided by the inductor, because inductor will have very small impedance, okay, and somewhere in the middle, okay, it's neither small nor large frequencies, then what will happen is that the impedance of inductor and impedance of this capacitor will cancel each other. So whenever we work in parallel circuit, it is more convenient to talk about what is called the inverse of impedance, which is called the admittance, right? We can add up the admittance. Admittance of resistance is 1 by 10. Admittance of inductance is 1 by j omega L. Admittance of capacitance is j omega C. Okay, so those three things you can add, and that will give you the resultant admittance, and then 1 by of that is the impedance. So you will see that at the resonant frequency, what is going to happen is that the admittance of inductance is going to be, as I told you, it is 1 by j omega L. Okay, so I have taken 10 milli. Okay, I think last time I took 1 milli, so let me just change to 1 milli. So,
yes, sir?
Yeah.
So are we supplying here 1 millivolt AC supply?
No volt. We are not supplying any volt. We are supplying a current.
So 1 milliampere.
No, yeah, 1 milliampere is the current that we are supplying.
Okay, sir.
Yeah. So if 1 milliampere is applied, and then the total impedance will decide what is going to be the voltage here, right? Current into the total impedance will give you the voltage. Okay, so since the components are connected in parallel, it is better to talk about admittance. So admittance is basically one inverse of impedance, right? 1 by Z is basically Y. Okay, so for example, the R1, let me call it as Y1. Okay, that is 1 by 10, which is 0.1, and then due to inductance, it is 1 by j omega L. So Y2 is basically 1 by j omega L. Now omega is a quantity that varies. So if you look at the resonant frequency, which is basically omega is equal to 1 by root LC. Okay, so if I substitute that, 1 by j into square root of 1 by j into 1 by root LC into L, so that if you look at, so that will be 1 by j into root L, and in the numerator C will come. So this will be basically C by L minus j into C by L. Similarly, if you find out the capacitor inductance, so it will be j omega C. Impedance, if you want to find out for capacitor, it is 1 by j omega C, but admittance is just j omega C. So you write j into then square root of 1 by root LC, j into 1 by root LC, omega I am putting the resonant frequency, and then into C. So what will be that? That is j into C by L, j into C by L. So Y2 was minus j into C by L, Y3 is plus j into C by L. So when you add Y1 plus Y2 plus Y3, that is the sum of the impedance due to resistance, inductor and capacitor. So Y3 will cancel with Y2, because one of them is minus j into root of C by L, the other is plus j into root of C by L. So only thing that will remain is 0.1. 0.1 is the impedance offered by, or the admittance offered by the combination. So total impedance is what? Inverse of that. Okay, so that Z is basically 1 by Y, where Y is Y1 plus Y2 plus Y3. Y2 and Y3 will cancel each other. So it is effectively 1 by Y is equal to 1 by Y1, which is what? Which is 10. So 10 ohm is basically the impedance offered by this. So to 10 ohm, you are basically supplying 1 milliampere current, and 1 milliampere will multiply with 10 ohm to give you 10 millivolt. So that is what you are seeing here. At the resonant frequency you have 10 millivolt. Now if you go to higher frequency than that, which will have larger or the admittance or the impedance offered by the capacitor will be very negligible, so it will be lesser than the total impedance will be, it is going to be lesser than 10 ohm. Okay, it will be lesser because it will be the parallel combination. The total impedance is determined by the smallest of the three, right? If you have 1 ohm, 2 ohm, 3 ohm, the parallel combination will have less than 1 ohm, because 1 is the smallest among 1, 2 and 3. Are you getting? Are you following what I am saying?
Sir.
Yeah. So if it is series, then it will be larger than the bigger one, right? But if it is in parallel, impedance will be smaller than the smallest one. So that is what you are seeing. So as you go to higher and higher frequency, the capacitance will drop down smaller, and therefore the total impedance will be smaller than the smallest, and therefore that will be multiplied with 10 or 1 milliampere to get whatever voltage you are seeing here. Okay, it would be 1 millivolt at some time, then it will be reducing further and further. Ultimately the capacitor will become a short circuit, so that it will be 0 volt. So that is what you are seeing at very high frequency from the resonant frequency. Similarly, if you look at the low frequency, the inductor will become a short circuit. Okay, inductor will become a short circuit, and its impedance will be very negligible. So parallel combination will give you effective impedance which is smaller than the smallest one. So this is the basic reason why you are seeing this kind of voltage. Okay, but somewhere in the middle, capacitor and resistance, their impedance will cancel each other, or you can say admittance will be, one will be plus, another will be minus, both are same magnitude, so they will cancel each other, and effectively it is resistive. And you will see, if it is resistive, the current and voltage will be in phase also. If you bring phase into the picture, okay, so if you bring phase into the picture at the resonant frequency, so here it is showing minus 180, and that's because the sign is downward. Okay, so that if you want to rectify that, I think you have to put a minus sign. So let me try to put minus. I don't know whether it will work or not. Yeah. So if you now look, it is I put minus 1, because minus 1, if I put, the effective direction is upward. The current is flowing upward. Okay, the sine wave is flowing upward from the bottom. It is going upward, and that is coming into the node. And you see that resistance, the phase of the voltage at the resistance is 0. Okay, at the resonant frequency. And when you move to the left, then what happens? At low frequency you are coming, and at low frequency, if you look at it has basically roughly 90-degree phase. Okay, so if you see, this is 100, this is 80, so roughly 90-degree phase. In other words, the voltage has a phase which is 90-degree leading the current. Voltage as a phase. What we are showing is the voltage. V means voltage here. So voltage as a phase which is leading the current by 90 degree. If you go to high frequency, we have minus 90 degree. Okay, that means voltage is lagging behind the current. Okay, so at high frequency, capacitor is what dominates, right? Because so capacitor, we know that current is leading by 90 degree or voltage is lagging by 90 degree. At low frequency, inductor is what is dominating. That is why voltage is leading and current is lagging by 90 degree. Okay, so that is what the phase information can give us. So if you remove the phase, you have only the magnitude, and it is plotted on a decades. Okay, frequency is plotted in decades, and here it is linear, 0 to 10 milli. So I told you how 10 milli comes also. Now you can go through next to the current. If you look at the current through the resistor, it will follow the same graph, right? Do you agree? If I try to plot this current, it will follow the same graph, same shape. Why? Because the current through the resistor and the voltage across the resistor, they are in phase. So if it is decreasing, both will decrease. It's satisfying Ohm's law. V is equal to IR. So R is a constant. So it is just proportional. Only the magnitude of the current that will be. So you can see here. Okay. So this is current. Okay, so here it is plotting with the same scale, that is why but the shape is exactly the same. But what do you think will happen with the inductor? Can anybody say, if I plot the current through the inductor, how will be it? For low frequency, it will be high value and then it reduces to small. Okay, something like a low pass filter. So that you can see here. Okay, so at low frequency it is 1 milli, and high frequency you can see it is, but there is a peaking. Okay, so that I will discuss little later, but there is a peaking also here, but you have to see that it is a constant at low frequency, and at high frequency it is 0. Near the resonant frequency there is a peaking. Now if I plot the capacitor, it will be just the opposite. At high frequency it will be 1 milli current. That means the entire current that I am supplying from the current source, it is going through the capacitor at high frequency. So if I plot it, so you can see this. Okay, and this is coming like this. Now if the peaking is very high, it is convenient to show it in the logarithmic, because in logarithmic it will suppress the amplitude. That is why we often use logarithmic. You can see that the peaking is suppressed. The peaking information is suppressed, and it amplifies the variation with respect to decade. Earlier it was seen like 0. It is actually very negligible. If you compare it with 10 raised to minus 5, 10 raised to minus 6, 10 raised to minus 7, they are all like very negligible quantities, but still it is amplifying the variation. So that's the difference between the logarithmic plot and linear plot. Okay, so when you want to take large details of small variations, we prefer logarithm, and also suppress large variation, then also logarithmic scale is good. But if you want linear, means it doesn't change with everything is in equal footing. Okay, so these are two different ways you can plot, but you have very huge peak here. Okay, but that this is just one decade. If you look at this is 10 and this is 1, so 1 to 10 is basically 1 decade. So that will be like a very small step in the logarithmic scale. Now if you have any questions, you can ask with respect to this.
Sir,
yeah.
So in case of inductor, sir, at the high frequency the voltage drop should be maximum also.
No. These are parallel circuit, right? This is a parallel circuit. So what happens is that when you go to high frequency, the capacitor will become very, very negligible. It offers negligible impedance. So all the current which is coming, it will just go through the capacitor. Nothing will go through inductor. So capacitor will act like a short circuit. If you are shorting, what happens? Voltage will be 0.
Yes, sir.
Yeah, so you look at the which curve, this one, the cyan color. Okay, can you see this one? I am putting this.
Yes, sir. Green one.
Yeah, yeah, not green. Green is this. I am showing this one, the top one on the right side.
Yes, sir. It is visible.
Yeah, so that curve is what showing the current through the capacitor. So current through the capacitor is how much at high frequency? It is the entire 1 milliampere, right? So this is 1 milliampere. The entire 1 milliampere is going through the capacitor. Why? Because this is like a short circuit. Okay?
Yes, sir.
So whatever current you are supplying, which is only 1 milliampere, so that 1 milliampere entirely go through this. So nothing is going through the inductor or even resistance also. Because 10 ohm is much larger compared to its capacitor's impedance. So that is why even through 10 ohm negligible current is going at high frequency, say at 10 kilohertz. Almost entirely, if you want to clearly see though this is appearing 0, it is not exactly 0. It may be something like 10 raised to minus 5, etc. Okay, so to see that you have to go to this logarithmic scale. So then you can see exactly how is it. Okay, so the current going through the inductor, that is red, it is basically very small. If you look at it, is 10 raised to minus 6. Sorry, yeah, 10 raised to minus 6. 1 into 10 raised to minus 6. So that is the kind of current that is going. And through resistance, there is a blue one, which is also something like between 10 raised to minus 5 and 10 raised to minus 6. But through capacitor, it is almost 1 milliampere. Okay, almost 1 milliampere. But some small amount of current is going through this red and blue. These are current through inductor and resistance. Okay, green is basically an voltage. Okay, that should not be confused with current. But except the green, all other three are currents. So if at any point of frequency, when you add these cyan color, that is the top one, capacitor current, then any frequency, you can take any vertical line and add these three, red, green and cyan. Red, blue and cyan, not green. Green is voltage. So red, blue and cyan color, if you add them together, you should get exactly how much? 1 milliampere.
1 milliampere, yes, sir.
Yeah. So it should be 1 milliampere, because that is what KCL says, right? KCL says the current that is coming into the node is 1 milliampere, then it is divided into 3. Of course, these are phasors, so they have both angle as well as phase as well as magnitude. So you can't just add the magnitude, you have to add with the phase. So they are complex quantities. So it will have real part and imaginary part. The current source that we have taken, it has 0 phase. So when you add, the phases should cancel and become 0, and the magnitude that you get ultimately will be 1 milliampere.
Sir.
Yeah.
Sir, can you also just explain once more about this resonance, how this occurring at a particular frequency?
Okay. So if you look at here, so resonance means what? Resonance means there is a frequency that the circuit prefer to operate in. There is a frequency the circuit prefer to operate in. So what is that frequency? That is what is given as the resonant frequency. It favors certain frequency. In this case, as I told you, it is 1 by root LC. Okay. So if you write here, so F0 is equal to If I say omega, it will be 1 by root LC, but if I say in terms of FC, F resonance, that is in hertz, it will be 1 divided by 2 pi, which I can write it as 2 star pi star then SQRT of L star C. So this is the formula. Okay, so 1 divided by 2 pi square root of LC. So if you calculate this, LE, it is 1 milli and C is 1 milli. So square root of 1 milli into 1 milli is basically square root of 10 raised to minus 6. Square root of 10 raised to minus 6 is basically 10 raised to minus 3, and this is in the denominator. You take it to the numerator, it will become 10 raised to 3 or 1000. So it is basically 1000 by 2 pi. So let me just, so this is equal to 1000 by 6.8. 2 pi is 6.28. And how much is that if you evaluate this?
Around 159.
Yeah. So 1000 by 6.28. Yeah, 159.2. 159.23. So that much hertz. 23 or 24 is better approximation. If I want to shift it, I can just. Okay, so that is a frequency that you are seeing here. If you look at, so this is now one thing also I have to tell how to take the correct value of frequency. Okay, of course you can take a cursor and find it out where the peak is occurring. For example, I go to this so this one, take a cursor, so one cursor I take, and then I shift the cursor to the peak like this. Exactly, if I match with the peak, then you can see that this is the frequency. So here I got 160. Our calculation is 159.4. Okay, some measuring error will be there, so let us ignore it. So we are getting the peak at the correct frequency which we expected. Okay, maybe I have not put exactly at the peak, maybe it is slightly, there is some measuring error like here. Okay, so it's very difficult to get it, otherwise you have to magnify and try. Okay, so that way you can do it.
Sir.
Yeah.
So then what about the resistance offered by the inductor and capacitor?
You should say impedance, right?
Okay, yes sir, impedance.
Impedance. Okay. So now another thing I want to discuss. So this is 1000. There are the lines are not equally spaced. You see the vertical lines? Can you see? They are not equally spaced. That is one feature of logarithmic scale. So after 1000, the next mark here is 10,000. So if you take the extreme right line of this too many closely spaced lines coming here, okay, the extreme right one is basically 100 hertz, and then the extreme right one here is basically 1 kilohertz. Okay, so can you tell me what is this line? This first line after 100 hertz, what is this? This line. This is your 200 hertz. That is how the decade, in the decade plot in the x-axis. So this is your 200 hertz. And the next line is 300 hertz. Next line is 400 hertz. So by the time we reached 400, we have taken a distance more than half. so it is not equally spaced. Okay, so 100 to 200 has a large separation compared to 200 to 300, and 200 to 300 has a large separation compared to 300 to 400. So that is how the frequencies are marked here, and that is why this peak is coming at 159. Okay, because the first line is 200, so it is between 200 and 100. Is that clear? Similarly, if you come here, this line and this line, if you look at the spacing, this is basically 1 kilohertz and then 2 kilohertz. Large spacing. Between 2 and 3 kilohertz, spacing reduces. 3 and 4 kilohertz, spacing again reduces. And if you come to 9 kilohertz and 10 kilohertz, that is the minimum spacing. That's the typical feature of logarithmic function. The differences get reduced as you go up and up.
Yes, sir.
Yeah. Now coming back to your question, you are asking about the impedance, right? Now if you want to plot the impedance, what you can do is basically so let me just delete all of this, delete the trace. So right click and you can delete the trace. Okay, so what I have right now is basically, let me come back to linear. Okay, so this is basically voltage at this node. This is the only unknown here. We can find out that unknown theoretically by solving the KCL equation, that current coming is sum of the three currents, current leaving, and then only unknown will be this voltage, and that you can find out. Okay, so now coming back to your question, so what is going to be the impedance? So impedance is basically what? It is basically the ratio of voltage and current. So here is the current. Okay, so if I take the ratio of the two, so I of L1 is basically the current, V of N001 is the label for the voltage of the node, N001 is the node name. Okay, if I want to give a specific name, I can give that also. For that I need to use this. Say if I want to name it as node P, okay, so I give P and then put it here. So then if I run it, instead of V of N001, it will be V of P. Okay, so if I plot this voltage, it will be V of P. Now, okay, coming back to your question, that is basically what is the impedance. So voltage by V of P by I of L1, that should give me the impedance. Okay, so V of P divided by I of L1, that is node voltage at P divided by current through L1. Okay, now you can see. So let me delete this one so that I will see the impedance. Okay, delete trace. Okay, then run it. So this is the impedance. Can you see the impedance? It is showing ohms. 0 ohm, 6 ohm, 12 ohm, 16 ohm. So as the frequency increases, the impedance. What is this plot? This is basically we are plotting basically J omega L. That is the impedance, right? J omega L. So as omega increases, J omega L increases. L is basically 1 milli. You just substitute it here. For example, how to get at 10 kilohertz. So omega is 2 pi into 10 kilohertz. right? 2 pi into 10 kilohertz. Multiply that with L, which is 1 milli. Kilo and milli will cancel, right? So what then will remain? 10 into 6.28. 10 into 6.28 is how much? 62.8. So that many ohms. So you can see that it is, so this point is 62.8 ohm. So it is just j omega L. Now if I plot capacitance, how will it be? For low frequencies it will be this. So that will be I of C1, right? I of C1. So same voltage divided by I of C1. So this is the capacitor impedance. Okay. Yeah. So let me plot both. So here I want to plot the impedance of inductor and impedance of capacitor. Okay, so one is like this and there is like this, and you can see perfect cancellation somewhere here where they are both equal. If you look at the phase also, phase we are not doing here, we are only showing the magnitude here, but phase also if you look at, you will see that they will match. In such a one will be positive and the other will be negative, so they will cancel each other. Here only it is showing magnitude, j omega, or you can say this is reactance, not really impedance. This is reactance because only magnitude it is showing. Any other questions?
Sir.
Yeah.
Sir, but it is not getting cancelled perfectly, sir?
No, this is showing magnitude. Magnitude. J omega L, that J it is not showing. J has phase information, right?
Yes, sir.
So the blue is showing omega L, omega into L, and the green is showing 1 by omega C, 1 by omega C, right? The cancellation comes with phase. Magnitude has to be same. So here if you see, if I magnify this area, the there is at one point the magnitude is exactly same. That is our resonant frequency. If I take a cursor and show, okay, let me put it here. So if I take this cursor and put it at the place where it is becoming equal, you see that it is a resonant frequency, 160. Okay, resonant frequency is how much? 159.29. So it is that frequency they become equal. Okay, now if I look at the phase of the current through L and the current through C, there will be 180 degrees phase. The one is going up, the other is going down. That is how the phase will look like. There will be 180 degree phase. Earlier I have shown one is plus 90, the other is minus 90. So between them the phase is going to be 180 degree phase. So 180 degree phase means one is plus and the other is negative, but magnitude are same, so they cancel each other.
Sir, can you please show the phase?
Okay, so phase, you have to go back original graph. Get the phase, you just run it, and then take this one. Okay, this one only has. So where is the phase? Phase and down phase. Yeah. So this is the phase. So phase is starting from how much? 0. Here it is starting from 0 and then it is going to, so I am plotting the current through L. Phase is 0 for low frequency and then it goes to 90 at the resonant frequency. So that is what I said. So if similarly if I plot capacitor, so this is minus 90, for capacitor it will become plus 90. Capacitor, you can see here, this is capacitor. So everything is getting, so let me just delete this. Yeah, so now you can see capacitor, it has 90. Okay. Because there are too many curves here, so it may be little difficult to visualize it. They are both same color also. So if you look at here, this is roughly how much? This is 180 degree, and here it is 0 degree. Can you see that? Here it is 0 degree and the phase is going to 180 degree. 0 then 180, but at the center frequency it is plus 90 degree. Plus 90 degree. When you plotted the inductor, what did we see? It started with 0 and then it went to minus 180 degree, and at the center frequency it was minus 90 degree. So if you look at the center frequency, for capacitor it is plus 90, for inductor it is minus 90. So the difference in the phase is how much? 180 degree.
180.
Plus 90 minus 90. So that is 180 degree. So that is why the cancellation happens. Magnitude is same, I showed you. Now I am showing you the phase also at the center frequency. So let me just suppress the don't plot magnitude. Okay, so now you can see the phase of capacitor. Capacitor current. Okay, phase of the capacitor current. If you want the phase, maybe it is better to plot impedance, or admittance also is okay. V of P. It is how much? 90 degree, right? Exactly 90 degree. Phase is exactly 90 degree. Now inductor. So this is inductor phase. Now if I show you, it will come minus 90 divided by V of P. Okay. So at resonant frequency, so resonant frequency was somewhere here. So let me take a cursor. Okay, so resonant frequency I have to go to 160, right? Somewhere here. Okay. 159 I put. So this is.
The current is not visible, sir.
Can you see a blue line here on the top?
No, sir, it is not visible.
Is it? Okay, then what I'll do is now. Can you see a blue line here? Okay, let me see whether I can change the thickness. Is it visible now?
Yes, sir.
Okay, so the blue one, that is this one, what is the phase it is showing? Here it is showing the phase as minus 89. This is for this is for the green one, okay, minus 89.94, and if you see it for here, it will be plus 89.94. Before that I need to take one more cursor, and then I have to go to the same frequency, 159. Okay, so now you can see phase here. So phase is 90, plus 90. Earlier it was minus 90, now it is plus 90. So they cancel each other. Why? Because the difference is 180. Magnitude, earlier I showed you, they both are same. Now I am showing phase difference as this is like a crust and a trough, coming together, and they cancel each other. But both the crust amplitude and the trough amplitude are same. You get the point?
Yes, sir.
Yeah. Now any other question? All right, so that is your experiment number 2, second part. Okay, now you will learn the theory in the network theory class, okay, sometime. Or what you need to do is just to write down the KCL and then find out the current through individual branch. You should get an expression for whatever graph I have shown here, and that expression will have complex quantities, so it will come as a complex number which is a function of omega. In magnitude phase form you can express it to see this variation. Okay, we can do that.
Sir,
yeah,
can you please upload the recorded sessions?
yeah, recorded session I will be uploading.
Okay, sir.
Okay, so now let's go to today's experiment. That is experiment number 3. So I will just save this. Parallel tone circuit. Okay, so now let's close this.
Sir, it is some part of experiment number 2, right, sir?
Yes, this is what I have asked you to do yourself last
Yes,
time. Because many of you did not respond, I am just showing it. But all of you should write it in the record book also. Okay, you have to implement it in multisim, or sorry, this LTSIM and LTSpice, and then I have shown you various things. So all these things you repeat and then write the formulas, corresponding formulas. Okay, find the current expression, just substitute the impedance as I told you. For series circuit you put impedance and then voltage source you are applying, so current will be total voltage that you are applying divided phasor V angle 0, whatever is the peak voltage. Last time I think we gave 1 volt, right? So 1 angle 0 is the phasor for voltage source divided by R plus j omega L minus j by omega c. That is your expression, and whatever L and C that you used, R that you substitute, so that will give you an expression for current. Then current is same through all the series elements, multiply it with its impedance, that will give you the voltage of each component, across each component. In parallel, what you do, you have a current source with say 1 milliampere amplitude, angle 0, that is a phasor, and then you find the voltage. So what is the voltage? Voltage is the admittance, total admittance you have to take. So y1 plus y2 plus y3, as I have told you, and then 1 by of that total admittance will give you the total impedance. So that multiplied by your phasor for current source will give you the voltage. Okay, then that voltage divided by the impedance will give you the respective branch current. So that you just work it out. Okay, so the third experiment is first order circuit transient response. So probably you might have studied that, right? Transient response. What are the topics you studied in network theory?
Sir, transient response yet not covered, sir.
Then what are the topics covered so far?
Maybe still doing nodal analysis.
Okay, nodal. So if you've done nodal analysis, you can do the previous experiment theory. It's all nodal analysis. For parallel, it is nodal analysis. The series, it will be mesh analysis. Okay, so that is good.
Yes, sir.
Okay, so what I am going to show, she will teach you. That is very much part of the syllabus. But right now, you can understand. I mean, these are very simple things. Okay, so here I want one capacitor. So this is an RC first order. If any of you have been present in the workshop, this was demonstrated in the workshop also. So I am just connecting it. We are simulating the behavior of this circuit. Again, every circuit should have a ground, so we need to give that. That is for software to understand, which is the reference for calculating voltage of the node. Now I have to give the value for this resistance. So let me give again 10 ohm. And capacitance, I'll give 1 micro. The micro is given by U. Okay, so that will be shown as micro here. Now voltage, I will give a pulse waveform. So right click, go to advanced, take the pulse waveform. Now pulse waveform has various inputs here. What should be the initial voltage? Okay, I can say that initial voltage is 0. Initial voltage is 0. And then what should be the on voltage? So let me say that is 1 volt. V is not really needed. Now, is there any delay in going from 0 to 1? If there is a delay needed, you can give that. Otherwise, you can say 0 delay. How much is the rise time? That means how much time it takes to go from 0 to 1. Okay, so if you want, you can give that. Say you can say 1 nanosecond. It goes very fast, 1 nanosecond. And then fall time, how if it was to come back, then again 1 nanosecond. But we are not going to, if you want, you can plot the number of cycles multiple times, but I am not going to do that. On time, say I would like to see this waveform for So let me just calculate. Response 5. Okay. So 5. Okay, 50 microseconds. Okay, 50 microseconds. I want to run this simulation for 50 microseconds. So I gave this details. So what I'm saying, it was at 0 initially, it goes to 1 without any delay. In 1 nanosecond it jumps up. If at all it is coming down, it will come down after 1 nanosecond. It takes 1 nanosecond to rise time, fall time. Okay, then I have to run it, right? I have given resistance, capacitor and source. Then I am running it. So I want to plot it for 50 microseconds. Then from 0 seconds I will start for transient analysis. So I am choosing transient here, and the maximum time step, say 0.1 micro. Okay, so let's so we want to see how the voltage is changing in the capacitor. So we are giving a 1 volt here like a pulse. It steps up. It's like a step function, unit step function, which you have studied. Okay, so it step up voltage from 0 to 1 at time t equal to 0. Okay, time t equal to 0, and then it remain up to 50 microseconds, and we are plotting up to 50 microseconds. So first of all, let me show you this input voltage. Can you see? It's stepping up from 0, that is with vertical green line, and then it remain at 1. Can I left minus 5 micro. Top I let me see 1.1, bottom minus 0.1. Yeah, so I hope you can see this. It is jumping from 0 to 1, and then it remain at. Is it clear? This is the input voltage. It just step up. If I wanted to introduce a delay, I can do that also. All I need to give is the third parameter, say after 5 micro. Then if I run it, so now you can see that from 0 to 5 microsecond it remains, then it is stepping up to 1 in a very short time. Actually it takes 1 nanosecond. Okay, so I think now it may be more visible. Can you see this?
Yes, sir.
Yeah. So that is the input. Now in response to this, the capacitor will respond, because you are giving a voltage to a series combination of resistance and capacitance. So how does the voltage on the capacitor change? Any idea? Any expectation how it will change? Anybody can respond. Unmute yourself, and what do you expect how the voltage on the capacitor to change? Even if it is wrong, it's okay. You can just Give a try. Anybody? Please do try. What is the expectation of the voltage across the capacitor?
Sir, 0, sir.
0. We are applying a voltage which is 1 volt at time 5 microsecond. So
sir, for a short duration.
For a short duration?
Yes, sir.
What will happen? So what will be the will there be any change in voltage? Initially it is 0 volt. So will there be any change in voltage when the pulse comes like this? Will there be any change in voltage?
Sir, there should be change.
How it will change? What do you think? Even if it is wrong, you can just make a guess.
So because for a very short duration of time, it is getting a very peak voltage.
Peak voltage. Okay, so let's see. So this is what we will see. The capacitor voltage gradually goes to 1 volt in a particular way. Okay. Now in your network theory class you will derive the expression for this. Now so this is with the 10 resistance value 10 ohm, capacitance value 1 microvolt. Now what I am going to do is I am going to make this resistance 100. What do you think will happen? What do you think will happen if I change it to 100? If I rerun it, what do you think will happen?
So current voltage across capacitor will get decreased.
Voltage across the capacitor will get decreased. Okay, so you note this, what you are seeing right now, and you will see that it is now 10 times slower. The way in which it is rising is 10 times slower. Now let me make it smaller. So I will make it 1. Now what do you think will happen?
So exponential rise.
Okay, so it will become very fast. Okay, the capacitor voltage almost follow up the input voltage change with a slight delay. Okay, it is able to come to 1 volt in a very short time. So as you increase the resistance value, so from 1 you go to 5, then it takes more time to rise up. Then if you go to 10, it takes even more time. You see that? You go to 20, it takes even more time. So as you increase your resistance, the time it takes to catch up with the input will be longer. Right?
Yes, sir.
You have learned that? Okay, so now I will keep it back to 10, the initial value. Now I am going to change.
Sir.
Yeah.
So is it the response that we are getting from capacitor?
This is the voltage across the capacitor, the blue. Voltage across the capacitor increases in this manner with time. That is what is called transient response. We have given an input. How does the output respond?
Yes, sir.
Now in signal sense system language you can say this is a linear system. to which you give this is the x of t input, and this is your y of t output. How to calculate y of t for the given x of t? So the input is basically a step function, but it is delayed by 5 unit. So u of t minus 5 micro, that is this. But what is your output? So if you know the impulse response, you can find out now, right? From today's class you have learned that. So we will try to solve such problems also in so you will get the theory even in signals and system also. Okay, so one thing you will notice is that as I increase the value of resistance, the time it takes to catch up to the 1 volt final value. Final value is 1 volt. It increases as you increase the resistance. Okay. Now I am going to increase the capacitance value. I make it 5 micro. Okay, I'm going to rerun it. Same thing. Reduce the capacitor value to say 0.5. Became faster. Reduce it further. Even faster. So what did you learn? If you keep the resistance constant and change the capacitor value, then the speed is proportional to the capacitance value, or as the value of capacitance increases, the speed decreases. Okay, not proportional, it is inversely proportional. The speed with which it rises up to 1 volt final value is faster if it is a small capacitance. I am not changing resistance, it is remaining at 10 ohm. Is that clear? Is it clear? Yeah. So what actually it depends on is the product of R and C. Okay. So time constant is given by R1 star C1. So the behavior of this circuit, that is the behavior of the output voltage, depends on what? It depends on the product of this resistance and capacitance value. If the product is same, I say now the product is how much? 10 into 0.1 micro. So that is 1 micro. Right? This is 10, this is 0.1. So if you multiply, you get 1 micro. I can have 1 micro in another way. I will make this one and this one I will make it 1. Now also the product is same, right? So if I run it, I should not change, I should not get any change in the output. So let us run it. You see, it's exactly the same, no change at all. But if this product becomes larger, then it will become slower. So either I can increase R or I can increase C such that the product is larger. So the time constant will increase if the product is increased. So if I make it 10, so now the product is 10 micro. So the product is increased, it takes more time. So that's why it's called the time constant. This product is called the time constant.
Sir.
Yeah.
So what is actually happening inside a capacitor?
So you are giving a source voltage here, and through a resistor you are connecting the capacitor. So you need to apply the KVL to see what happens. So the input voltage is basically sum of voltage drop across resistance plus voltage drop across capacitance. Initially the capacitor has no voltage. So all the voltage that is applied here will be coming across the resistance. So you can see that also. So you measure like this, click here, then bring it to here and release. So this is the voltage across the resistance. So at time 5 microsecond, when you have the pulse going to 1 volt, entire voltage is now on the resistance, because capacitor has no voltage. Only when the capacitor gets charged, the voltage on it will rise. Q is equal to CV, or V is equal to Q by C. Right? So what will be the current if the entire voltage 1 volt is coming across the resistance? The current will be voltage, which is 1 volt, divided by 1 ohm. So that will be 1 ampere current. Okay, so let us plot the current also. So current is just exactly like the red curve. So they are, so you can see on the right side it is 1 ampere current. So that 1 ampere current will flow and bring the charge into the capacitor. As a result, the blue curve will begin to rise. So which means the voltage across the capacitor is now rising. Earlier no voltage was there, entire 1 volt was across the capacitor. Now charge has flown into it because 1 ampere current flowed. After some time, lot of charge came, some voltage, say for example 0.2 volt is reached here at around 7.4 microsecond. You have 0.2 voltage across the capacitor. So what is the voltage across resistance? If it is 0.2 voltage across the capacitor, only 0.8 voltage will be coming across the capacitor, right? So you can see that it is 0.8 here. When this rises, that goes. Sum of these two will always be 1. That is KVL. 1 volt is equal to voltage on the resistance plus voltage on the capacitor. So that will always be 1. That is the proof of KVL. So when this one rises, that one reduces, and when that one reduces, the voltage reduces, what will happen to the current? Current is basically that voltage divided by 1 ohm, right? Whatever is 0.8 volt divided by 1 ohm, that is 0.8 ampere. When it becomes 0.6 divided by 1 ohm, that is 0.6 ampere. So the current gradually reduces. So the rate at which the voltage rises will also reduce, because only less amount of current is bringing the charge. The amount of current coming into the capacitor is less, or the charge coming into the capacitor is less. So the rise of voltage in the capacitor, initially it was faster, but then it slows down, because the voltage across the resistance is smaller, which decides your current. So the current reduces, and the rate at which the voltage change on the capacitor also reduces. If you have large current, faster change, because more charges come to the capacitor in less time. That is what we mean by large current. Clear?
Yes, sir.
So all of this behavior is determined by the product of R1 and C1. So what are the things I plotted? I plotted basically the voltage on the capacitor, that is a blue curve, and then I plotted the voltage on the resistance, which is the red one. So to see the red one, I need to delete this let's delete this. So this is the voltage on the resistance, and then current through the capacitance, or which is same as the current through the resistance, which is like this. Now if I remove it from 1 volt, then I can see both. So what I will do is that I will make this go to 10, and this one I will say make it 0.8. So now the product is 8, 10 into 0.8. So now I show the current. Oh, then also it is coming the top. Okay, so it adjusts itself. The axis is adjusted itself. So okay, is it understood? Is there any doubt? I will not be discussing this anymore. If you have any doubt, you have to ask now. But you can ask your doubts in the WhatsApp group.
Yes, sir.
Okay. Alright, so the second part of this experiment is an inductor and a resistance. So this is RC. First, it is called first order RC, transient response. Now, first order could be an RC or an RL. So let's save this. See, RC transient. So again you take the voltage source, and then take an inductor, rotate it, then a resistor, connect it with wire, these two circuits have many things in common. So for our convenience I will take 1 Henry, and this one I will take 10 ohm. Maybe, or I will take 0.1 Henry, 0.1 Henry and 10 ohm. Then again I need a pulse waveform. So I go to advanced, choose the pulse and specify initial value. Initial value is 0, final value is 1. So delay is say 0.1. Rise time, keep it very small, 1 nanosecond. Fall time, even if you don't specify also it is okay. Then bond duration I will keep say 5 seconds. So this is my voltage. Okay, so now transient analysis is what we are interested in. So you choose the transient analysis. Stop time. In this case, okay, so let's see if I keep 5 seconds, how does it look like? Maximum time step, say 0.01. Then vertically align. Okay. So I have not given any rise time. Okay, so it took some rise time, which is not what I wanted. So I'm going to specify rise time. 1 nanosecond. 1 nano is enough. Fall time also 1 nano. I don't want this slow rise. Okay, so here you can see what is that we are seeing? We are seeing the voltage on the resistance reaching. So let me just come at it again. First of all, let me run this and then adjust the window vertically. See the input first of all. So input is at 0.1 second, it goes to 1 volt all of a sudden. Okay, actually it is taking 1 nanosecond, but in the scale of second it is abrupt. And then I am looking at what is the voltage on the resistance. So that is this green. It is almost catching up very fast. So earlier we have learned that if you increase the resistance, it would make it delayed, right? So let me try increasing resistance. No, when I increased the resistance, what happened is that it became even faster. Now let me decrease the resistance. I made it 1. So when I made it 1, then it slowed down. Okay, so let me make it even smaller, 0.1. Then it became even more slower. So here things are not happening the way it happened in the last experiment. In the last experiment, the voltage on the capacitor was rising at a speed which is determined by the product. So if the product of R and C was larger, it takes larger time. If it was smaller, it used to take lesser time. But here when you make it smaller, it takes larger time. Okay, so making things smaller, here making things slower here. So that is one thing. Now let me look at what happens with L value. So now it is 0.1. If I take it say 1, it becomes smaller. Slower. So from 0.1 to 1, 10 times I increase, it becomes almost 10 times slower. So then I should make it smaller, 0.01, very small. Then it became faster. So as I increase the L value, the delay increases. So now I can say the time constant is equal to it is proportional to L, but it is inversely proportional to R. Okay, so this is what you need to learn from this circuit. Here the time constant is L by R. As you increase the L value, time constant will increase, it becomes slower. You go to 1, it becomes slower. Okay, but as I decrease, make it 0.1, say, it becomes faster. Whereas if I increase this to 1 ohm, when I increase this, what happens? Denominator is increasing. So it is 0.1 divided by 1, which is 0.1. So you see that roughly it takes 0.1 to go up. So L by R is basically give you an estimate of the time it goes. An estimate, not exact. Estimate. Exact value you can't say. It is asymptotically going, but it will reach almost 70%. It will reach in L1 by R1 time. So if you increase L1 by R1, that is what it determines. So here L1 by R1 is 0.1. Now I can make 0.1 in so many different ways. I can make this as 10 and this as 100. So that also L1 by R1 is 0.1. So I should not have any change. So you see no change. So it depends on L by R value. But if I reduce the L by R value, now it become, sorry, if I increase the L by R value, it will delay more. So 10 by 10 is 1. Earlier it was 0.1, now it is 1. So it will increase. Okay, is it clear?
Yes, sir.
Okay. So here the time constant is L by R. Earlier it was R into C. Both are first order circuit. Now what is happening here? To see what is happening here, it is a good idea to look at this voltage also. So you see the voltage, what happens? The voltage is initially very large. Almost the entire voltage applied comes 1 volt across the inductor, and then gradually that voltage reduces and reduces. So let me make this also 1. Okay, you can see this. So blue is the voltage across the resistance, red is the voltage across the inductance. Sum of them is basically KVL, that gives you the voltage across the voltage source, and that should be equal to 1 at any time. If you add these two voltages, you should get 1. Now if I find out the current through the resistance, it will be same as the blue curve. Current through the resistance, it will be overlapping. It will just come upon it. You see that. Okay. Now if you look at this curve, it is not very smooth. That's because the number of points are less. So you can increase the number of points by reducing the step size in the simulation. So now you see that the curve is more smooth. Okay. So current through the circuit, voltage across inductance, voltage across the resistance is what you have. Any question, any doubt about this?